Okay, so we are um, we are looking at optimization algorithms, and we have seen in the last lecture that this is a general framework of any descent direction method. Okay, what are the elements we had? We have this descent direction. We need to find in each iteration, and then either we call it a step size or learning rate more appropriately, parameter alpha. We need to determine that. Then we update the current position from theta to theta theta k to theta k plus 1 in kth iteration. And there is one more thing: we stop algorithm when the termination condition is satisfied. What we have seen the last lecture is this part. All right, and today we look at termination condition first, and then we go to this important part, finding the descent direction. Are there any questions from the previous lecture on finding learning rate? Anyone? Yeah. Okay. If there are no questions, let's start discussing about possible termination conditions. Okay. When do we stop algorithm? That's important, and when we will be okay. So as you can guess, and most of the times when you're implementing any algorithm, we fix the number of iterations beforehand. So that is one criteria. That let's say either we fix the number of iterations, or we fix the maximum amount of time, t max. Once say 1 hour, we want to run the algorithm for 1 hour and terminate there, and then the number of iterations can be random in that case, and no matter what is the case, we stop and we look at the output. And this is a very, in a way, blind way to do it. And can someone tell me like what could be the possible drawbacks of this method? Anyone? Well, that's one thing, and we don't know whether it will doesn't have time to converge. Yeah, there are two possibilities. Like we don't know when whether it's converged or not, and if it is not converged, it will stop even before that. We don't know where we are. Um, so that's a problem. But on the other hand, there is a in many situations you have this time constraint, because each time when you're developing algorithms, each iteration takes some complexity, running time complexity, and you can't afford to wait until it will settle down. So depending on what application we are looking at, maybe we need to do this, and that's why still it's a popular in many cases, particularly when you want to test, like quickly have some idea what is happening. You look at it, and when uh, it is not converged, and if you intuitively feel that it's not, you let it run time, and you do until you're quite happy with it. We will see an example where different algorithms behave differently for same k max. Okay, and if suppose you can let the algorithm run and let it terminate it after some time, uh, condition on what is the state of the function value, then the first option in that setup is called the condition is absolute improvement. Okay, what is this? It's exactly as the name suggests. It's the difference in the function value is insignificant. You take epsilon a, which is very small, say epsilon a is 0.1 or 0.001, 0.001. Okay, once the function value is not changing very much, then you stop the algorithm. Sometimes what people do is that you take consecutive like a 10 iterations, last 10 iterations. Over the 10 iterations, this difference in the function is not very significant, then you stop it. That is just a step more complicated than this. One has to be very careful when you have this kind of setup, is that you might actually can get stuck at saddle points. Saddle points is generally a big deal, but you can very well, in this case, functional value doesn't change even when the algorithm is moving towards the minimum value. It doesn't change. So during that one iteration, if functional value didn't change much, algorithm solve, but you're not nowhere closer to the minimum value. Okay, one should be careful with it. And so this, that is first condition where algorithm solves based on function value. And the second one uses gradient, because in each iteration, the algorithms we are looking at, we compute gradient. So why not use the gradient value to actually decide? As you can guess, at for function at local minima, the gradient is at local minima, gradient supposed to be 0. And so when you're very close to 0, you stop it. So again, you fix some value, say 0.01 or something for epsilon g. And when gradient value is gradient length of the gradient is smaller than this epsilon g, you stop it. And again, it can have a similar effect as a saddle point. As you can see, even when you're moving in this direction, if the gradient is 0, close to 0, then you might end up stopping the algorithm. Then the third condition is a relative improvement. Okay, we see with an example why this condition is useful. And this essentially says that if the difference, okay, the difference is relatively smaller than epsilon r. Again, epsilon r you can fix 0.01 or more than, smaller than that. Okay, and but it considers what is the value at that point. Let's look at where this relative improvement can perform better than the other two approaches. Let's consider this these two functions. One is theta 1 square plus theta 2 square, and the second one is shallow. As you can see in the this is f1 and this is f2. As you can guess, because this multiplied with 0.2, this is more shallow around where this minimum is achieved. Around the center, it is shallower. So the gradients doesn't change very much. How relative improvement will actually help in that kind of situation where you don't know whether the function, loss function, is shallower or not. Okay, you want your algorithm to work well with both cases. And if you look at, first, suppose if you apply absolute improvement condition, okay, and it says that this is a theta space. Suppose you fix the error tolerance as 0.1 in all three cases, then you can see that this is a plot of two circles. First one, f1, which is which has a deep this one, it's a blue curve, which is deeper at the center point, where minimum point, and f2 is shallower. You see that you need to be very close to the minimum 0 comma 0. That is a minimum a point where you achieve minimum. For F1, for the same value epsilon a, absolute improvement demands you to be within that circle, which is very small compared with the circle corresponds to F2. This is correspond to F2, and this is a smaller circle is F1. So clearly, absolute improvement is not working well with for both the functions. Now let's look at a gradient magnitude condition. Again, we can actually for epsilon g equal to 0.1, we can compute what this the circles will look like, and you can see that again there is a huge difference between circle corresponding to F1 and circle corresponds to F2, right? And so when you are applying this condition for shallower functions, you terminate before you are anywhere closer to the minimum point. Now look at relative improvement. Particularly this for these functions, it's you can observe that this relative value of the function, in fact, same for both the function. So you end up seeing both circle at same point. Okay, and so for the same epsilon, you have same circles, and that's the interesting part about relative improvement. And if you are looking for an algorithm which can work both on shallower and deeper functions, then you can go with the relative improvement. Again, we can't fix in advance when it will happen. So one has to be careful with that also. That is about termination conditions. Let's look at most important part of this chapter is first order methods. That is finding the direction D. Any questions on termination conditions? Please go ahead and post your question if you have anything. Okay, first method is we call it gradient descent. We can also some people also like wants to specify more steepest descent method. Throughout the talk, we just use gradient descent. That means naive way to do gradient descent, and the main idea is to move in the direction of steepest descent. How do we do it? What is the inspiration for it? Suppose you are at theta 1, which is not optimal, okay? And so let's look at here. This function, this Rosenberg function, which has a global optimal at 1 comma 1, okay? You started somewhere, say, this is theta 1. Suppose you pour some water here. It will always takes steepest descent direction, and it flows somewhere and finds a way and goes all the way to minimum. That is the inspiration for this method. But one need to observe that water can change its direction at a infinitesimal scale. It's a nice way to follow the water, but we can't do it because if we do small changes in its path, we need to compute gradient in each step, and it can be complex. So what we do, we fix a length of each step. And let's see. So let's denote throughout the this talk. Let's denote GK. Denote the gradient at theta k by GK, and this is the steepest ascent direction. So by applying minus, we get steepest descent. by normalizing, we are saying that we take one step, unit length, and by then unit length multiplied with learning rate, we will see that. But the descent direction length is a unit by normalizing it. So as I said, if I fix the if I multiply this descent direction by very small value, say alpha is equal to 0.001 or something, then you can expect this algorithm to behave like water, okay, moving slowly. We will see that in a simulation afterwards, okay. But if you take alpha more, say 0.1 or even 1, okay, for these values, we are essentially saying that take this much length here if it is moving like this, okay, long. So many times you end up seeing this kind of behavior in gradient descent because you don't want to make small steps. And also one more observation one can make here is that when you use exact line search in each step, okay, you are at theta k, and you know what is the descent direction. You want to find the learning rate optimally using exact line search. There is a question here. Uh, it might be addressed later, but why is it that the termination condition for the gradient descent depends on the thetas, whereas those you just described explicitly deal with the function values? And where is the termination condition here? I didn't understand. Where is it? For all these algorithms, you can have a different termination conditions. I was just having a look at the relative improvement equation. I'm wondering if the numerator on the left-handed side, okay, where is it? Is this the equation, Krishna?
Yeah, that's the one.
Yeah.
Yeah. Oh no, sorry. Yeah. No. The one where
No,
it's divided
no,
by.
no. Think about we always move in a decreasing direction.
But if for some reason it does increase, then the
Yeah.
algorithm will get terminated.
Yeah, but which algorithm you think we can move, increase?
Yeah, I guess so.
Do you have any algorithm that might actually
I
happen
don't
this
have a
way?
specific example. I was just wondering if that
Yeah,
was.
yeah, that is true. But you can very well apply mod if
Yeah.
that is a concern.
Okay, so we can have the absolute value. It doesn't
Yeah,
matter.
yeah, it doesn't matter.
Thank you.
I think Matthew has answered your question. Yeah, that's what Matthew said. Back using exact line search by solving this formula. then what you see is that the directions are orthogonal to each other. You zigzag, and even if you don't do exact, even if you're close to exact, you might end up seeing closer to zigzag um, paths in gradient. Can you hear me? Okay, thank you. Okay, if you have any difficulty following this proof, let me know. It's not very difficult. It's just observation that we are taking h to 0. And this order of h square comes from the fact that we are using Taylor expansion. Um, yes, that is correct, Len. You can use different conditions. You can even say that the gradient difference also smaller than certain value. You can use that also. As long as you believe that either something works for you, you can use it. We cited only the gradient magnitude condition, right? Which one? I didn't. Which condition you are equivalent to? Okay, I can't see why it is, but I'll think about it. Okay, so you end up saying a zigzag pattern if you use this. And let's look at an example where I have taken a function called boost function. And this is one of the test functions used in optimization, and where I have run simulation. You can see that for gradient descent, where I used exact line search and started here, we ended up seeing zigzag pattern, and it converges. It takes around 10 iterations to converge for this simple case. And all right, and as I said, if you want to really imitate water flow, you want to take small steps. And if you see, for the same algorithm, if I do with alpha 0.001, you can notice that the path is very smooth. It's just like flowing. Sorry, I'm using a wrong color. Okay, this blue curve, you can see that it is converging, but I had to use 10,000 iterations to come to this point, okay, which is still far from the optimal value. Whereas for exact line search, I already here after 10 iterations. So you end up paying a lot of cost, because if you take small steps in neural network, particularly backward propagation and forward propagations are very complex and in the time consuming. So it's not really possible to implement such a smooth thing. And if you use anything bigger, it oscillates. So we need to figure out a better ways to do. The next one is called conjugate gradient. As I said here, once you enter, there is a chance that you zigzag, and you see later that that is in fact is the case with gradient descent. And to remedy this situation, there is something called conjugate gradient. So in the gradient descent, we have this zigzag uh, way of traveling, wherein this what we do is that we use the notion called conjugate of directional directions and the consecutive iterations with respect to matrix A. This is the condition for two vectors, dj, di, and dj being conjugate to each other, conjugate with respect to each other according to matrix A. Okay, and we use this condition A A is supposed to be positive semi-definite, and which is the case when you have quadratic function. So this algorithm is for us to propose for quadratic functions. Quadratic function is of this form, and I'm sure you guys are familiar with that. There is, okay, there is no question. So again, just like a simple case in the gradient descent, we again use line search here. What happens when we use that? Using line search in each iteration and alpha like this. Okay. Um, you are at kth iteration, then you know theta k by then, and all you want is that compute theta k, like find what is theta k plus 1. You have theta k, and alpha is something you want to learn now, alpha k, and dk is already given to you. Then how do you find this one? As you can know, you just minimize for alpha and find that alpha that minimizes alpha k. And once we have it, we know theta k plus 1. In quadratic, for quadratic functions, computing this alpha becomes very easy. In fact, it's when in kth iteration, this implies that alpha k is d power k a theta k plus dk dk dot product with a dk. Okay, this is the formula. It's easy to compute. Once you have this, then you can actually find beta k just using the property that the next direction is conjugate with dk. Then beta k becomes, if you use that property, beta k becomes this, and this we can compute exactly. Okay, so we start with gradient descent. Like gradient descent, we just start with the steepest descent direction, and we update theta 2, and then after that we apply recurrently with alpha k and dk update and dk plus 1 update, and by using beta being this, because we know a exactly, matrix a exactly for the quadratic functions. This is example, small example. Are there any questions so far on conjugate descent direction method? Conjugate gradient, sorry. You mean here? Let's see why it is. So just think of you're at the second iteration. Okay. Um, you already have theta 2 at okay, in the first iteration. From the first iteration, then you can compute g2 from this, the gradient, that is minus. Okay, and then we have already d1, so we need to compute beta k, that is computed from here. What do we choose for the matrix? Okay, we already assumed in this case that function is a quadratic function. We know a, all right, and of course that is a constraint on conjugate gradient, that if it is if it is not a quadratic function, it is not straightforward to apply. There are some suggestions on what we do for finding beta. Okay, we approximate beta k, which is possible when it is a quadratic function. We replace with two options. One is Fletcher-Reeves approximation, and the other one is Pollock Ribiri. I don't know how to pronounce, but yeah, these are the two options. And when you have non quadratic function, you can go for it and check which one works the most. And but in this example, again we took this Booth function, and that is a quadratic function. If you look at this, each term can have at max power 2. So it's a quadratic function. You can exactly compute beta k, and you can exactly compute alpha k in each iteration. Then it's easy to implement this algorithm. And look at this convergence. Surprisingly, it converges in 2 steps. And for quadratic function of uh, nth order dimension n, this here we have dimension 2. For quadratic function of nth dimension, it converges in n steps. That is well-known fact. That is advantage. But again, it applies to quadratic functions, and when it comes to non-quadratic functions, it's a tricky job. Anyway, overall, there are some challenges posed by these gradient descent methods. Let's look at them. The first challenge is that selection of learning rate can be very difficult. We have seen like there are several methods we studied, but all of them have their own advantages and disadvantages. So overall, the learning rate is finding learning rate is a difficult task. And Benoit has shown us in one dimension case how taking learning rate very small can be a problem, as well as if it is learning rated too high, it can also be problem. Similarly, we can see in the two-dimensional case, here I ran gradient descent, the naive gradient descent, two values. One is being uh, alpha 1 being 0.2, and each step I'm updating, decreasing like this. And you see that it's actually global minimum is somewhere here, and it is terminated very quickly. Uh, and other hand, if you take alpha 1, initial alpha being 2, and again apply the same decrease for alpha k, you see this jumping around even before coming anywhere closer to it actually oscillating so much. And this is the problem even in two-dimensional or multi-dimensional case. Okay, and again this function, this particular one is Rosenbrook function, which is not quadratic. So applying conjugate gradient becomes very difficult in this case, and we can see the similar effects here. One option could be that make learning rate, you actually specify in advance how do we change learning rate. Here what we did, we blindly decreased as follows, but you can make some more assumptions like I will reduce uh, learning rate only when the there's a gradient, the length of the gradients is smaller than certain value, or function values below certain value. You can do that. Again, it's not a smart way to do it. It can, no one can guarantee that you will reach that small value. That algorithm certainly reach that small value. So even that kind of adjustment can be a problem. And one more important thing is that in all we have this kind of update, theta k plus alpha dk. Whatever is the direction, we are using same parameter alpha. It's a scalar for all coordinates. So yeah, the same thing for k plus 1, ith coordinate for all I, we have same scaling learning parameter. So by actually having a different learning parameters for different parameters, we can actually make better progress and improvement. We can improve the algorithm. That is one thing which is essential for the algorithm we are studying now. And this is a point we already spoken about. It's about saddle points. So gradient descent methods, as we see later, like this, and valleys and closer to saddle point, it oscillates. It doesn't really converge properly, and it doesn't really understand which direction it has to go, and that is one complexity. So again, we illustrated with Rosenbrock function, and we can see that if you apply gradient descent, even though valley is like this, okay, one would like to have an algorithm which somehow understands this valley and goes along it rather than jumping around this point, and that is what gradient descent does. And so we want to be a little bit more smarter on this. And yeah, so keeping these issues in mind, there are several ideas proposed, and we will look into them in increasing order of their efficiency. Or yeah, first thing, a first approach is that adding a momentum to the method. Can anyone say why momentum makes sense? Can someone quickly say that, okay, what is lacking in gradient descent, and by adding momentum, how we actually uh, make it? We already discussed that. Anyone can say something about momentum in general? You guys familiar with momentum in physics? Because the yeah, that's so let's look at this. Okay, suppose you have a slope, and think of this as a ball, and if you leave this ball, because of gravity, the velocity changes. This displacement is not same at each time. Okay, here displacement may be smaller in first 1 second, but the next second it might actually move much more, and so it much more. So this is essentially captured by in physics, momentum is denoted with p, and mass into velocity. So we don't see that. So think of each iteration is run for 1 second or 1 minute, and that's the time. uh, so in each iteration, the ball, the displacement is not constant across the iterations, but in gradient descent is the case. So we need to add that momentum, the change in the velocity. That is done. If you look at just this is the next point where you are, and theta k is where you are currently. Okay, we want this quantity to increase when you're moving on a slopey path. Okay, until you reach the bottom, maybe somewhere here, at least until you reach the bottom, you want this to keep changing the difference between these 2 points. That is a magnitude of velocity. How do we update velocity? So this is the formula. Why it is actually keep changing the difference between thetas. If you look at if you start with the v of k being v of 1 being 0, and then v of 2 is actually beta, that is 0, minus alpha into g power 1. Okay. So if you write recurrently, what will happen is that vk plus 1 is equal to minus alpha I is equal to 0 to k beta k minus 1 g of I. Okay. If you notice, this is an increasing value because every time you're moving until you reach the point somewhere here, okay, it will be increasing point. Yeah, that's correct. It actually has it remembers. It has to remember to get the momentum because uh, if ball starts here and if you have a different ball which starts here, okay, by the time the green ball comes here, the momentum of green ball is much more than the red ball coming here. So you need to retain that memory. And that is what happens using the velocity vector. We retain by taking summation over this. As long as you are moving in a decreasing direction, this will add up and the direction, the displacement keep increasing in each iteration. That is essentially motivation for momentum. But can someone say what could be the issue with this? What happens if you keep exactly? So if you have this function, it is nice and all. If you global minimum, suppose it is like this, the ball comes and if it is traveling for longer, it will shoot up because it doesn't know where it is going. So we need to actually make this ball a little bit smarter by letting it know that when you're closer to this point, suppose you're here, the next point will be somewhere here, and you need to tell it that it's actually overshoot if you move too much. That's what happens with the Nesterov momentum, where we do instead of earlier. So g of k is f of theta k, right? And in momentum method, we have this condition as a first equation, alpha gk. This where gk is gradients here, so that is vk minus alpha theta k gradients of fk. This is the current location, but you know that theta k, which and vk can be computed wherever you are because you know vk by then, you know beta, that is some fixed value, and theta k is current position. So it will be always ahead of you. Suppose you are here, this is theta k, and theta k plus beta vk will be somewhere here. Even though it is not the next point, it is somewhere between. And if you are here, then that next point will be somewhere here. This guy will come here if theta k is here. So you know whether you will be overshooting or not. That's why you can slow down when you reach the bottom, and that can be captured by this update. And it's the same step, just like a momentum, adding momentum. Okay, what time is this? We will have a break exactly after 6 7 minutes. No, not break, like we have discussion after 6 minutes, and then 5 minutes break and we'll come back again. So you can look at how it works if you take this function once again. We here in this plot, we are actually showing all three methods. This is first one, the blue curve is naive gradient, where is steepest descent direction, and that is GD. And one the red curve is with momentum, and the green one is with Nesterov momentum gradient descent. You can see that the last method, Nesterov momentum actually is better. Here I'm fixing number of iterations, and if you let it go, it might reach. And yeah, if it doesn't reach, you need to adjust the learning rate parameter a little bit, and you can make it work. But you have a better method now. Yeah, are there any questions so far, or any suggestions? Did anyone go through the exercises I'm giving in the lecture notes? Are there any difficulty with the lecture notes? And okay. I think we can have a break now, and or how much time we have? Yeah, we can have a break before we start ADA grade. Um, I'll be here for 5 more minutes before my break, and if you have any questions, we'll be happy to take. We'll start again at 6 here, like a 5 here. That means 6 on the timetable in 10 minutes approximately. Is this fair?
Yeah, that's it. Thank you.